for positive x. Do both of you begin the question by taking in that information and the significance of it? So that's a,
Yeah, try to.
yeah, so that is really useful because so often the restricted domain simplifies the question. So when you realise it's all positive values of x, then you don't have to worry. If you do a sign diagram for an inflection and it's 0 or less, forget it. Or you don't need to use it. So quite often, so I'm jumping ahead really, but if you, what's this? I have trouble with my computer freezing and they've promised me a new one, but it hasn't come yet. All right, so, all right, so if you do, I can't draw on top of my, I'm just showing a document that I can't, I might draw on it this way, I wonder. Common markup tool. Well, that works. Okay. So if I do an imaginary derivative of the function, so this is totally imaginary, and you know that there is a restricted domain, do that. Draw a little wall on your sign diagram so that even if you find out -2 is an inflection point, it is not part of the domain. Don't worry about it. So Pete, do you want to, Pete and Hannah, are you comfortable with showing on your sign diagram the parts that you don't have to worry about? And Hannah, 2 students aced the test. The majority of students were around, below and just above the C mark. So when I sent that email, I believe that most of this class are understanding the work and I would have expected them to pass, but students found this quite a challenge. So Hannah, I don't know if that's a comfort. Yes, exactly, Hannah. That's what I feel. I feel that there were several students in the class who did not display the understanding that I believe from their weekly work that they have. And that is a nervous pressure, I think, of stage 2. And I'm very hopeful that once this first SAT is behind students, they say, I know there's time pressure. I know the level of the SAT. I know how much preparation I need to do, and hopefully one SAT out of the lot is not really going to affect the overall grade unless you're going for an A+. A+ students must start at a high level from the beginning. All right, so we've fooled around with that. And now, if we look at, we've got to find from the graph. Now, sometimes we bold those things to help students notice that you needed to write the coordinates of stationary points. Well, there is only one stationary point on the black graph, and it's at 1, and you look at the scale, it looks like 2 3/4. So a lot of people, yes, here we go, a lot of people said 1 and approximately 2 3/4. Then check the stationary coordinates of the stationary points of the function and confirm the exact value. When I read exact value, if there is an irrational number like e, I have to leave the e there. I don't use my calculator to evaluate it as 2.1. All right. So to check it, we've got the equation y equals ex on x, and we differentiate it. Now I'm going to sort of assume, tick both of you, are you confident with the quotient rule? Excellent. So you differentiate it using the quotient rule, and you get this formula. And when I look at the denominator, I see x squared, which is positive for all values of x. All right, so the denominator is positive. It can only equal 0 when the numerator equals 0. So you factorise the numerator. What do you know about e to the x as a function? The value of e to x.
So that function must, if that function, no, because that function equals 0, e to the x must equal 0 or x must equal 1.
Yes. All right, Hannah, do you agree that there are two possibilities to make the function equal 0? So it's easy. If x equals 1, 1 take 1 is 0. Can we look at my little sketch of the function e to the x. See how it is totally above the x-axis. Can the function e to the x equal 0?
No.
No. That bit of information you're going to use over and over again. So there is only one value where that function can equal 0, and that is when x equals 1. All right? So when x equals 1, if we put 1 into the original function, that gives us the y coordinate. And if we go back to the original function, which is written up higher, all right, 1 on x, e to the x. So 1 on 1 is 1, e to the power 1 is just e. So the y coordinate is e. All right. So most of the class got 2 out of 3 because the easy bit, the reading off the graph, they left out. So part B, on the axis above, sketch the graph. Now this was a non-calculator question, so that was pretty tough. G of x is 1 on x squared e to the x. So that was a very, very tough question. And the best way to do that was just to plot a couple of points, just to put a couple of values in and get the shape from 3 or so values. Always when x equals 0 is an easy value to plot. All right, so that's how I could see that that's what students did. And you can see in the solution that, no, you can't really see in the solution how they got that plot. But that is the easiest way to do it when you're not allowed to use your calculator. And label with M the stationary point. So you knew that the stationary point was 1e, and if you'd done a sign diagram, which we didn't show in the solution, you would have seen that the point was a local minimum. All right, so here, part C. And Pete, I'm assuming perhaps that this is the point at which you really wanted some explanation. This is where we begin a conjecture. Now, the way this question is written, you don't know that it's leading to a conjecture, which is perhaps a deficiency in the way the question was asked. So as you complete this table of values, to work out the stationary point, you need to have a gradient of 0. So you're asked to work out, let's reread the question, complete the following table and coordinate of the stationary point. So you've got to find the gradient of this function, which you've already done, and show that the gradient is 1. So when you find the derivative of 1 on x squared e to the x, the example here went straight to the cube function because I squeezed that in. So that if you look at part B, I've found the derivative of the g function, which was e to the x. Sorry, 1 on x squared. So that is, yeah, so that's already the derivative there. and that was 2. So part B, so these two parts, you'd already been directed to complete them. So we do it again for 1 on x cubed e to the x. So just quietly have a look at finding the derivative, product rule, e to the x is e to the x. Just write down x cubed minus, write down e to the x times the derivative of the denominator function. So that's 3x squared, all divided by the denominator squared, so x to the power 6. So again, it's the numerator that makes the function 0, and a stationary point is when the gradient is 0. And if we take e to the x out as a factor, and I actually took out x squared as a factor as well. So if x equals 0, 0 times e to the x will be 0, but remember that 0 wasn't part of our domain. Remember that x was strictly greater than 0. So we got rid of it. That possibility is not in the domain, and therefore x equals 3 is the only possible value for the stationary point on the domain. Are any of those comments giving you a bit more detail of the thinking as you do this problem? That's excellent. All right, so your guess was quite good, Hannah, and you got them right. And actually, seeing you say that reassures me, because many students got it right with no working. And I was a little bit concerned that maybe calculators had been used. But you saying you just guessed it actually makes me feel a bit better, that students did, as the supervisors did make sure students did not use calculators. Now, because that was blank, because students use their intuition, you hadn't practiced the process. So the practice for the process of the conjecture is absolutely essential. So instead of doing it with n equals 1, 2, 3, so let's just go back. So x to the 1 would be x to the n, so n equals 1. X squared, so n is replaced with 2. Just see that the n is replacing the power on the x. So the things that I want you to notice about making a conjecture. Quite a few people made a pretty good attempt at this, but they just said that the stationary point was at n. Now that is probably worth 0, because the conjecture has to be in general. So in general, for the function stated and the condition, the n, that's meant to be an integer symbol, I believe. So n is an element of positive integers. So some people write n is an element. The z is the integers, positive integers. So that's not very easy to read. Or n is element of the real. Oh no, so it does have to be integers. So n does have to be a whole number. I hadn't noticed that myself. Then the location of the stationary point, so that's what the conjecture is all about. The location of the stationary point only for this function, not for any other function, has an x coordinate. Now, lots of people left that out. Has an x coordinate equal to n. Does that detail help you a bit with how you express the conjecture? You've got to repeat all that information that you're given. Yes, Peter?
Sorry, that was meant to be a tick.
Oh, no worries. Okay, now to prove it or disprove it, what we did with the actual number n equals 1 is we found the gradient, and if the gradient was 0, that is where the stationary point occurred. So here we have a function that we find the derivative of. Well, you just leave the n's in there. Just remembering that n is a number. So the derivative of e to x is e to x, and you multiply it by x to the n, minus, you just write e to the x down, and you multiply it by the derivative of the denominator. So that's n x to the power n take 1. So you can see that my pattern of using the quotient rule is slightly different to the pattern of the solutions here. And then it's just divided by x to the n all squared. Are you comfortable, both of you, that x to the 2n is the same as x to the n all squared? I'll write that on the side. X to the n all squared is the same as x to the 2n. Hannah, are you happy with that? Yep, that's good. All right. Sometimes these tiny little things when we're under pressure are what trip us up. So if we can make that numerator equal 0, then we'll have a stationary point. What we did with the actual numbers 1, 2, 3 for the power of x is we factorised it, knowing that e to the x is positive and knowing that 0 is not in the domain. So if you look at that numerator and we take our x to the power n take 1, all right, the lowest power on x is n take 1. So if we take x to the n take 1, I'll do this on the bottom of the screen. X to the n take 1 e to the x is actually a common factor. So to get x to the power n, we have to multiply by x minus, we've got n lots of the factor that we took out, minus n. Therefore, the only way to make this equal 0 is for x to equal n. So when x equals n, we have a stationary point. The derivative will equal 0. And therefore, that was our conjecture. Our conjecture was that the stationary point has an x coordinate equal to n. Do you follow all the reasoning involved and sort of the pattern of the reasoning? We have silence. No, no, no. So to me, the pattern in general is have a look at the original information and internalize significant features. So internalize that the function is positive for all x, that an exponential function is always positive. Then the guidance of particular values is going to be useful in making your conjecture. So the way you work out the answer, so we're looking for the x coordinate of the stationary point, and the way we work out a stationary point is because the gradient is 0. So for every single value, we are looking to find the stationary point, and we're looking to find when the gradient is 0. And the pattern for every single point was that we factorised the numerator. And what we found when we factorised the numerator is that first factor could only equal naught if x equals naught and x is not in the domain. So that was not a possibility. So it was actually the little linear factor. So I'm just looking down here. X minus 3 is a linear factor. X minus 4 is a linear factor. So it was the linear factor that we made equal 0. So we're already hopefully seeing and internalizing the pattern. So you make the conjecture using all the information already given. So I'll just bring that up. So the conjecture as we read it is in general. A conjecture has to be for all values. It's related to a function, it's got restrictions on the domain, and there's some sort of relationship that we're trying to find, that the location of the stationary point has an x coordinate equal to n. Most people who are successful in understanding the pattern get the second half. They get that the x coordinate is equal to n. The rest of it is really just giving context to your conjecture. Do you feel a little bit more comfortable with developing a conjecture?